Hello and welcome everyone to this morning's lecture. My name is Chris Myers. I work in the Cornell Center for Advanced Computing, and I'm going to be describing to you today, providing you with an introduction to the Python programming language and ecosystem. As noted on the previous slide, any questions you have can be posted in the chat at any time during the talk, and I'll try my best to answer those. Please complete the survey that will be emailed to all registrants afterwards. We appreciate the feedback that you provide for us, and we expect that links to this recording and to the slides will be sent out to all registrants usually within a week. So with that, let's get started. If there are any sort of technical issues that come up, please also mention those in the chat. I'm going to cover four sort of broad topics in this talk today, and the primary emphasis will be on Python as a programming language, and so talking about some of the syntax and keywords and sort of the design philosophy of how Python operates and how we can use it to accomplish various tasks. Python is also a very large and rich ecosystem of packages, and so I'll talk a little bit about that towards the end, although I'll be giving a more detailed talk on that in this series next month. I'll talk some about the programs that we use to run Python code, interpreters, various kinds of interpreters. Is it possible to make the slides bigger? I can try to zoom in here. Does that help at all? It might mess up some of my later slides, so I might need to toggle between different settings here, but we'll play it by as we go. And then at the end, I'll provide some tips on installing various Python packages and some of the tools that support that. I'm not going to go in the order that I just described, because I kind of need to set up this first part, which is talking about Python as a program, and that's because there are different kinds of programming languages, and I'm addressing here the difference between compiled and interpreted languages. So compiled languages, of which there are many, are written. We write code in some language, and then we process that by a compiler that produces an executable or some standalone application that we can run. And most of the apps that you might run on your computer are things that are already compiled and are executables. On the other hand, interpreted languages, of which Python is an example, as are many others that you might have had some experience with, are processed by another program, which is called an interpreter, that runs and executes program statements. So in an interpreted language, each statement is executed sequentially, and this is very useful for doing interactive analysis and development and prototyping, developing new algorithms or new workflows. But interpreted programs are typically slower than for compiled languages, and so what we're really doing is kind of trading off faster development time versus potentially a slower execution time when we actually try to run these things. So there are many different Python interpreters. Sort of the core one, the default one, is known as Python's formerly known as CPython, and might sometimes be installed as Python 3 on your computer. And that really forms a basis for a lot of different tools. So IPython is an interactive an interpreter that sits on top of Python that provides additional useful functionality for interactive work by adding these so-called magic functions that provide additional functionality, but they're not part of the Python language itself. Jupyter is a system that many of you might have had some exposure to or experience with. This is a notebook-based software system that can process Python code. It actually uses the IPython kernel to run that Python code, which of course then is sitting on top of the core interpreter. But there are other kernels that support other languages that can also be run within Jupyter. In addition, it's possible to embed the Python interpreter within other programs. And so, for example, there's a new beta release of the Excel, Microsoft Excel, that's embedding parts of Python to allow you to sort of script parts of of Excel workbooks in Python. And there are other programs such as the ParaView visualization program and other things that basically embed Python as kind of a scripting engine within these bigger environments. And then there are various other sort of non-C Python based interpreters that are out there, but I'm not going to be talking about those. In fact, this talk that I'm giving you is running within a live Jupyter notebook. It may not necessarily look like a Jupyter notebook, but it is, and we can run our first bit of code here, if assuming this has run correctly, where I've turned the pretty printing off. And so I will be throughout this talk sort of running some Python code alongside of commentary describing what I'm doing. So just briefly, some history and background. Python was created in the early 1990s by Guido van Rossum, and he built this really as a general purpose language, not constructed to support any specific problem domain, but to be generally applicable. And that's in contrast with some of these other languages that I've mentioned that are built to support specific kinds of environment, kinds of calculations. So a lot of the useful functionality for specific application areas is actually not part of the core language itself, but is brought in through a wide variety of third-party packages that Python provides support for developing. And really, it's the Python language that is the substrate for tying all the different pieces together that when we build up large programs and computations. So in my opinion, Python is very well designed. It's intuitive, it's readable, and it's practical at the same time being expressive. It's kind of elegant in its design. It's free and open source, unlike some of these other languages that you might be working with. And it's important to note that the scientific computing community was an important early adopter of Python when it was released for a variety of reasons. Some of you already have some programming experience, maybe in other languages. Some of you may be trying to learn some of the basics of programming. So I'm just going to sort of try to mention a few key programming concepts that arise really in any language, but then sort of show you how they get implemented within Python. And so programming is really the act of creating a set of instructions that lets us build potentially complex data processing pipelines that can transform maybe some input data and act on it and produce some outputs according to some set of defined operations. And within these pipelines, there are sort of typical components. There are data types and data structures, which are really sort of the stuff that is passing through the pipeline that is being transformed. There are functions and methods and operators and things that are the operations that are carrying out these data transformations. We use variables as names to associate with data and functions so that we can sort of make code more understandable both for ourselves and for others. And then we often organize these pipelines according to different control flows and sort of blocks of code that get executed in different contexts. And we'll sort of visit these things as they arise in Python. So there are a number of built-in data types in Python. And this is typical of lots of programming languages. There are sort of numeric types, integers and floating point numbers and complex numbers, as well as logical types, true and false, Boolean types. There are things like character strings that allow us to represent text, containers and collections, which are data structures that allow us to hold multiple groups, sets of data in a collection. There are file objects, functions and classes and modules, as I'll describe to you later. Basically, everything in Python is an object, and so they all sort of fall within. But these are some of the built-in data types that are here. And then there are built-in operators for acting on data. So numerical operations that addition, subtraction, multiplication, so on and so forth, as well as various logical operations. And then as an object-oriented programming language, there's support not just for using these built-in data types, but for creating new data types. And we'll look a little bit at what that consists of. I don't know why I'm having trouble driving. My slideshow is not working very well here. But so, for example, we can add two integers. So these are the integers 2 that I'm adding with the plus operator. I can actually use the same plus operator to add two strings, but addition here with strings consists of concatenating them rather than doing some other kind of arithmetic operation. And then, of course, we can use sort of parentheses to group various kinds of calculations. So, for example, we can, why is that not going? Now I'm going to have to make my screen smaller so I can see this, right? Okay. So we can group things together and use various arithmetic operations to carry out more complicated kinds of calculations. We can define variables and assign them values in Python, and this is done in Python and using what's known as dynamic typing. So in Python, variables acquire whatever the type of whatever data is assigned to them, and the assignment operator is this equals operator. So if I say x equals 3, then 3 is an integer, so x, at least for the moment, is of type int. It's an integer. But then I can turn around and say x equals 3.14, and now x acquires the type of a floating point number, a float, or I could assign it to a string, and then its type will change again. And so this is compared to static typing, where we have to sort of pre-declare what the type of some variable, say x is, and that then a compiler may say, or some other tool might report an error if data of a different type is assigned to that variable. So this dynamic typing is often used in interpreted languages, while static typing is often used in compiled languages. It's worth noting that since Python version 3.6, the ability to provide type hints has been included in Python so that you can actually write Python code that suggests what type different variables should be. This does not impact the running of the code, but it can be used with external tools for type checking or for documentation and other things. And so you might come across some Python code that actually, even though the language is dynamically typed, does provide some of these type hints, and that's what's going on there. And then, of course, we can assign values to variables and then carry out the same kind of operations and expressions like I was doing before. So we can, for example, add x plus y, and in fact, even though x is an integer, y is a float, but the sum is a float, and so this z acquires the type of whatever evaluates on the right hand side, which in this case is x plus y. As I mentioned, Python is an object-oriented language, and what that means a couple different things. It means that there's support for bundling together data and functions into more complicated kind of data objects that have a kind of an internal structure. And there's also support for defining new data types that can represent different type of abstractions or concepts that are useful in different problem domains. So there might be, in fact, within the Python ecosystem, there are new data types that get defined by different packages, such as arrays or data frames or networks or models and so on and so forth. So Python is kind of practical in its object orientation. It also supports other kinds of programming. But as I said before, everything in Python is an object. So it has a type or a class. It has a value associated with it. It might have some attributes, which are data defined in association with objects. It might have some methods, which are functions that are defined in association with objects. And then it's got a namespace that organizes all those attributes and methods. I mentioned that there are built-in container types in Python, and this is sort of the core set of them. We'll sort of look at some of these in more detail in some code examples, but there are different ways of bundling data together into ordered lists or into dictionaries that map from a set of keys to associated values. There are sets that support set algebra that's very useful for certain things. Tuples, which are sort of ways useful for bundling collections together in an immutable sequence, and then strings, as I mentioned, which are essentially sequences of characters that allow us to represent text. And then there are other kinds of container classes, such as arrays and series and data frames that are very useful, that get defined in some of these external packages in the ecosystem. So everything in Python has an object, so we can, for example, query the type of an object. So this statement here at the beginning, x equals bracket 1, 2, 3 bracket, creates a list, and we can ask what is the type of x, and we are told that it is a list. The dot operator, this little dot here, allows us to access elements in an object's namespace. So one of the methods that's defined on a list object is the append method. And so we can now, for example, append 4 to this list and then print out its value, and we see that now we've appended 4. And in fact, if we want to look at the list of all the names in a namespace, we can use this built-in function dir to see. And for example, we see that there's this append method that's there, as well as some other things that we can do with lists. So as I mentioned, Python is readable. Python code is perhaps more so than some other languages, and the readability of Python code was an important goal in its design. And it does this in sort of a slightly non-standard way, in that it uses indentation to identify code blocks that implement sort of code structure. So for example, if I want to loop over a set of integers, I want to loop over something, say 10 times, I would write a statement such as this for I in range 10, and then I would indent, and everything that's sort of consistently indented underneath this for loop becomes part of the thing that gets run in the loop. Whereas in another language, say in C or C++, I would use curly braces, I would use additional syntactic elements to delineate what is the code block that gets executed repeatedly. So if you're just starting out, sometimes inconsistent indentation can be kind of a gotcha, but it does, once you get the hang of it, and once you sort of use code editors that support that consistent indentation, then it does sort of make things less cluttered when you're trying to read it. This indentation works with other kinds of structures. So if we have some kind of if else block, if x is greater than 0, we want to do something, otherwise we want to do something else. Each of the blocks within these clauses gets indented, whereas in other languages, say in MATLAB, there are additional keywords that are used to indicate when we reach the end of such a thing. Whereas in Python, there's no keyword that indicates that we've reached the end of one of these clauses, just the change in the indentation that supports that. Control flow, as I mentioned, is an important aspect of programming. There are different kinds of control flows that go on in programs. There's looping and iteration. We'll look at some examples of that. There's branching of the sort that I was just mentioning. And then there's also things like exception handling, where we try to deal with errors in a useful way. Iteration is an important aspect of lots of programs, especially for scientific computing, where we might be iterating over big data sets or repeating calculations many times to generate statistics, for example. And the for keyword in Python allows us to loop over every element in some collection, but it defines collections rather. What can be looped over is rather sort of broadly defined, and it can essentially iterate over. And you'll see this in documentation. We'll talk about iterables. An iterable is something, essentially anything that can be looped over, can be iterated over. So we might have an explicit list, and we could, for example, loop over each of the elements in the list and print them out A, B, C, D, E. Or we could loop over all the integers from 0 to 9, so a total of 10 integers, and access those values. And again, that's what the for keyword is one mechanism for generating these kinds of loops. I think I'm going to skip through this right now. It's a sort of we might come back to it if there's time, but it's sort of an aside on what this range function is actually doing. But we'll just skip through this for now. There are other iterables we can iterate over. So I mentioned, for example, that there are dictionaries which map keys to values. So in this dictionary, I map the letters A, B, C to the numbers 1, 2, 3. And then I can ask, for example, what are the items of this dictionary? And it's actually stored in this object called dict items that are sort of contain these pairs of keys and values. But then we can, for example, loop over that object, that dict items object, and print out, say, the keys and values. And this is a way of iterating over this more complicated type of thing, but it sort of knows it carries with it the internal logic of how to do that iteration. Many programming languages, including Python, include not just for loops, but also while loops, and the keyword while enables you to loop over a code block until as long as some condition is met. So in this little bit of code that I've written here, I'm going to choose random numbers between 1 and 365, and I'm going to keep doing that until I find the same number is found twice. And so for those of you who maybe you've studied a little bit of probability theory, you might recognize that this is sort of an example of what's known as the birthday problem, since there are 365 days in most years. But now if I execute this, what this does is that it chooses a random number, it creates an empty set of things that have been found, and it says while R is not in found, so while the random number that we've chosen isn't already in the set, we will continue on in this loop. We're going to add R to found, we're going to generate a new random number, and this run through, it took 21 times to find to find a pair of random numbers that matched between 1 and 365. Of course, this is a random process, so if I ran it again, I would get a different number, and if I ran it again, I get a different number. And if you were actually interested in studying the statistics of the birthday problem, you'd want to sort of bundle this up in a function that you could call conveniently and repeatedly many times to build up a distribution. And if we have some time at the end, I have an example kind of showing that. There are, again, along the lines of sort of readable notation that, the compact notation that is at the same time readable. There are what are known as comprehensions, different kinds of comprehensions, such as list comprehensions or so on and so forth. And this is a mechanism basically for taking that for loop and kind of squishing it all into one line. So for example, if I wanted to, I can create a list of in this case, squares. And what this says is create a list that contains the values n times n, so n squared, for n in range 10. So it's going to loop over from 0 to 9, and then it's going to stick into the list the square of each of those integers. And that's, again, I can do that in one line now, and once you understand kind of what that looks like, it sort of makes things more readable than if you were explicitly writing out that for loop. And I can add additional conditions. So if I only care about the squares of numbers that are even, I can add an additional if clause here and create a list of even squares, which is just the squares of the numbers, say from 0 to 19 that are even by checking n mod 2 equals 0. That will filter out just the even numbers. And then there are also dictionary comprehensions. If I want to create a dictionary on the fly, I can use a similar notation using curly braces instead of these square braces. And so here's some code that, for example, imports a module from the Python standard library, the string module. So I talked before about built-in data types. Those are things that are there in Python as soon as you start it up, but sometimes we have some other code that we want to be able to access. And the way we get that into our current working session is to import them. So we can import, for example, the string module. Oh, we've got some beeping out in the hallway. I hope that's not a fire alarm or something, but we'll see. Hello, everyone. I'm back, and I'm glad to see that there's still, I wasn't sure how many participants I might see in the list upon returning. Let's see. Yes, there was a fire alarm. So let's see, it's 9. I was probably out for 15 minutes. I can either try to sort of cut through some stuff, leave some things out that I was going to cover, or I can go over. Does anybody, how do people feel about that? Should I just kind of continue from where I am, or should I try to finish up? Would rather we finish it all. I've got 2 votes for finishing it all, but please.
Do you want people to thumbs up or thumbs down, do a reaction?
I don't know how to do that. Finish all. Okay. I'm getting lots of, yes, we will have the recording, and I know that we can edit out the 15 or 20 minutes that was not so interesting when I was out of fire alarm, but I will. Okay, it looks like there's a lot of interest in finishing, so I will continue. So I was talking about comprehensions, and I was creating this mapping. So I created a dictionary here called mapping that maps each letter in this set of ASCII letters in the string module. I did it just to the index in the list, but we could map these things to anything. But again, I can create this mapping all in one line using this kind of compact comprehension notation. Error handling is a sort of a, and not all languages provide great support for dealing with this, but Python actually does quite nicely. You could be running a program that's going on for several days, and maybe you're dividing, one number by another, and then and you might expect that you're never going to divide by zero, but in some cases that might actually be the case, and so you could have something running for a few days, and then all of a sudden you'll encounter some zero division error like this. You can't divide by zero. So in this case, I'm just looping over this list 5, 4, 3, 2, 1, 0, and it's printing out these divisions. But then I try doing 1 divided by 0, and it throws this error. So if you just have code like what I've written here, that program is just going to crash and stop. Even if that wasn't your intention. I mean, that obviously wasn't your intention. But one of the nice things that Python provides are try except clauses that allow us to try a statement and then actually catch the error. So in this code below, what I'm doing is, instead of just doing the division 1 divided by a denominator, I try to do the division, and if it throws a zero division error, I can catch that and just print out, say, cannot divide by 0. But the program will continue running. The program doesn't stop running because I was able to catch that and recover gracefully from it. And that's a very useful thing. And it's sort of part of the Pythonic philosophy. Instead of checking first to see whether the denominator is 0, I just try something. And if it doesn't work, then I can go on from there. And there are lots of different exceptions that can be caught. So I might have some code, for example, that tries to open a file and read all the lines in it, such as I've shown here. But if I try to do this with a file that doesn't exist, it throws a file not found error. And again, my program would just kind of stop at that point. But what I can do instead is I can try to open it, and then I can catch explicitly, I can try to catch a file not found error. And then when I do this, it tries to open this file that doesn't exist, and I print out a little error message saying the file does not exist. But I've been able to catch it and recover from it rather than sort of suffer through these. So if you do try running code and you encounter some sort of runtime error like this, you can work with try except clauses to try to capture those. An important part of any kind of programming language is the ability to define functions that carry out particular tasks. And in Python, the keyword def is used to define a function, and the keyword return is used to return a value from that function. So we call a function with some inputs, we get an output or potentially multiple outputs, and the indented function body is whatever it is that we want to do to implement that, to carry out what that function does. And we can optionally include a docstring, which is what's enclosed here in red in these triple quotes, a documentation string at the start of the function body that can be used as documentation for the function. So here's a function called concatenate that takes two strings, string 1 and string 2, and some separator. Although the separator is optional in the sense that I provided a default value, which is just a single space. So when if I run this code, now that the function is defined, we can call it. So for example, I can call concatenate with two strings, A, B, C, D, E, F, and I haven't passed in a separator, so it uses the default separator, which is the single space, and it returns the concatenated string with a space in the middle. But I could provide a different separator by providing a third argument. This would override that default argument. And so in this case, I've decided I want to make the separator two dots, and so now I get this other string returned. If I'm willing to sort of write everything out, I can pass in all three of these arguments in whatever order I want, by using what are called keyword arguments. So I can specify a separator and a string 2 and a string 1, and now when I run that, I get my concatenated string with the separator that I've specified. And keyword arguments are very useful, especially if you have a function that's got many arguments, and maybe you just want to override one of them and you want to use the defaults for a bunch of them. Then providing keyword arguments is key. And as I mentioned, I wrote this docstring, so I can, for example, within Jupyter, I can ask about concatenate by putting a question mark at the end, and it tells me about this function that I wrote. It tells me what the signature, the arguments are, and it shows me this doc string. And I'm sorry, I'm having some scrolling problems at the bottom here, but it's basically printing out this documentation string. And so by writing these documentation strings, these doc strings, you can kind of keep track, even for your own code, keep track of what things are doing. Let's see. Sorry. So I've shown you some of the building blocks. I've showed you how to assign data to variables. I've showed you how to build up some of these kind of containers like lists and dictionaries. I've told you how to define functions, and what the programming language does is it lets you put all those basic building blocks together in whatever combinations you want in order to carry out some computation of interest. So I'm just going to give you sort of okay, we got a question here. Is Python a case-sensitive language? Yes, Python is a case-sensitive language, which means that uppercase and lowercase are different things from each other. So if I were to say, you know, import with a capital I, it would complain because that's not a keyword. The import is with a lowercase I is a keyword, but not with a capital I. That's a very good question. And I think most programming languages these days are case-sensitive, but there are certainly some that have been developed that are not. So in this, I'm going to put some of the pieces together that I've been showing you to make us a cipher. A cipher is a little device for encrypting text messages. And this is a Caesar cipher because it was something, it's apparently similar to what Julius Caesar developed, thousands of years ago, to encrypt messages so that his enemies couldn't read the communications. And it was a rather simple cipher compared to what we have now for encrypting messages, and that it basically just sort of took the letters in the Roman alphabet and shifted them by some amount, and we'll see what that looks like. And so we could build up a little Caesar cipher. We could import this same string module and access the ASCII letters, and then we're going to write a little, is that going to work? Oh yeah, here we go. Write a little encoder. So the letters are just these letters, the lowercase and uppercase ASCII letters, and then the encoder is just a dictionary that we create with one of these comprehensions that maps each letter in this sequence to a letter that's shifted over by 3. So, and it wraps around the end. So A, if I could backtrack, so I'm doing this because I'm saying letters, each of the letters, the ith letter gets mapped to the I minus third letter, but then I mod on the length of the whole list. So that enables me to wrap around the back. And I do that for all of the letters in the list. And so A gets mapped 3 back, which goes around the back of the list to X, and B to capital Y, and C to capital Z. And then once I get to D, then it's just three letters to the left. So basically what this says is for every letter in this big string of lowercase and capital letters, I'm going to map it to some different letter based on this code. This is just a code for encrypting a message. And then I can write a function, a simple function called transform message that takes some message I want to encrypt and a code, which will be one of these dictionaries, and it transforms a message using a code dictionary. And I've written out a little doc string here. And basically all this does is it kind of loops over each of the characters in the message, and it builds up a transformed message, T message, which I get by getting the mapped character. So if it encounters an A, then that's going to get the value associated with the A, which is capital X, and it's going to replace A with an X. And then once it's gone through the whole message and transformed everything, then it will return the thing. So for example, I can take a message such as I come to bury Caesar not to praise him, and I can encode that using my encoder and then print the encoded message, and we see that message has been encrypted to this kind of gibberish that I can't read without knowing how to decode it. It turns out that decoding this is not so hard if we actually have the encoder, because we can just sort of work the dictionary in reverse. Remember, the dictionary maps keys to values, and if that mapping is 1-to-1, I can always just write something that maps the values back to the keys, which is what I've done by writing this little dictionary comprehension for the decoder. And so now if if I look at that, then I see that now the capital X maps back to the A, the Y to the B, and so on and so forth. It just reverses that thing. And so, for example, I can decode the message if I know what the right decoder is, by sending in this encrypted encoded message with the decoder, and I get back my original message. And that was how, that was how these ciphers were used originally by Caesar and his collaborators. So one of the things that I talked about object-oriented programming, and I talked about the ability to define new data types, and we do that in Python by defining classes, a class, and we use, in fact, this class keyword to define a new type of data, a new class. A class is a template for creating instances of some particular data type, and it lets us define what that data type consists of. And so in this case, I'm going to define a new data type, which is a shift cipher. And this is like the cipher we just looked at. But if you think about the code I was just showing you, it was a little complicated because I had both an encoder and a decoder, and I had a set of letters, and I had a function that transformed the message, and I had to make sure all those things were working, could work with each other. And what object-oriented program lets us do is build new data types that bundle together both the data, the encoder and the decoder, along with methods that can act on that data, such as this transform message. And I won't go through all the mechanics of this, but I use the same def keyword to define now methods that are attached to a cipher. I can encode it, I can decode, I can build up these decoder, I can initialize, I can create a new one. And so I can run this code, and then we can create different ciphers with different shifts from the same template. So for example, I have my message here that I showed you before, and I could create a shift cipher where I shift everything to the left by 3, such as I showed you before. So that would be a shift of -3, and so I can create a cipher, underscore M3 -3, and then I can say encode that message. This is the encoded version we saw before, and then I can decode it with the same cipher, get the decoded one. But then I could create a different cipher instead, maybe that shifts everything to the right by +7, and so that would be a shift cipher 7. And I'm first creating an instance of this thing that he calls that init method that we saw on the previous page, and then I can call different methods on this, such as encode and decode. And when I do that, I get now, this is a different cipher, it's got a different encoder, so I get a different encrypted message. But then when I decode, I can get back to where I was. And so this is an example of how we can use object-oriented programming to bundle together different data and methods into kind of a coherent thing. And we can reason about what a shift cipher does. It takes a shift value and it can encode and decode, and we don't have to keep track of these separate pieces of data that need to work together in order to carry out various operations. And that kind of thing is again, lots of third-party packages in the Python ecosystem will define new classes, new types of data that have different functionality that are useful for different things. And so even if you yourself are not writing code to define new data types, it's important to know how to work with objects of different data types that get defined in different packages. So for example, what would happen if I intercepted an encrypted message that I suspected had been encoded with a shift cipher, but I didn't know what the shift was? Well, one thing I could do, for example, is so let's say there's some message that got encoded. I don't know what the shift was, and so all I know is this thing here. I get this message, and I say I don't know what that means, because I don't know what the shift is. But for example, I can write a little loop. I can loop over a bunch of different shifts and create a shift of that with that shift value, and then I could decode my encrypted message, and then most of these things are not the right shift, and so they just transform one piece of gibberish to another. But I can scroll down through this thing, and I can actually find a message here. So a shift of -8 actually decodes this encrypted message to something that I can interpret. And so this is sort of a very crude form of code breaking where I'm sifting through different possibilities, different ways of decoding some encrypted message using these same kind of elements, these programming elements that I was showing you. Just very quickly, curiously, there's a module in the Python standard library called this, and if we import this, we are shared with this little meditation by Tim Peters called the Zen of Python, which sort of talks about some of the philosophy of writing in Python. I'm not going to go through it all here, but curiously, if we actually look at what is inside this module, which we can now in Jupyter with double question marks, we see that it's actually the Zen of Python is itself encrypted in this gibberish text, and that it's got a slightly different way of implementing the decoding, but it's essentially a +13 shift that is then modding on the 26 letters of the alphabet. And so the Zen of Python is itself written as a shift cipher, and then when you import the module, you get the decoded version rather than this encoded version. I think that's kind of fun. But then that's the kind of stuff I think is fun. So in any case, so I've been talking about elements of the programming language and how we can use them to sort of carry out different computations. And I want to talk a little bit about sort of running Python code, because I mentioned there were different ways, different interpreters we could use. So if I have Python code and say a program, a source code file, myprogram.py, and we use the .py file to write Python code, I can just run this program, say from the command line, by saying Python myprogram.py, and whatever series of instructions are in there will get executed. That could be a very short thing, or it could be something that runs for days. And that's a very useful thing if you don't need that interactive access, if you just want to be able to run something that you've programmed. I mentioned IPython, which provides this kind of enhanced interactive access, and then Jupyter Lab and Jupyter Notebook, which are these sort of web-based environments that allow us to merge together code and documentation and graphics and results of the sort that I've been showing you here. I did want to plug an upcoming talk in the series. So the next talk in the series by my colleague Christopher Cameron will be on using Jupyter Lab in the cloud for Python. We have a question in the chat. What is your favorite IDE for Python? So an IDE, for those of you who don't know, stands for Integrated Development Environment. And as its name suggests, it's an integrated software environment that allows you to write code and to run the code, say an interpreter, to inspect data values. I'm very old school. I write my Python code in Emacs, which is a text editor, and I typically am running that when I'm, say, debugging things in the IPython console or in a Jupyter notebook. But certainly a lot of people use more modern tools. VS Code, Visual Studio Code, is something that a lot of people seem to like for working with Python, and it supports other things such as auto completion and the like. Someone says, where does Spider fit in all this? Spider is an IDE that is available. It's sort of part of the Anaconda distribution that I'll mention a little bit. Spider, it seems, I mean, it's more, I think it doesn't get as much sort of development attention as some of these other common environments, such as VS Code or PyCharm is another one. I mean, I've used it for both my own work, as well as I've used it for doing training sessions like this, where it's useful to be able to have everything kind of in an environment. So you could certainly use Spider, but if it doesn't provide the support that you like, then there are these other things you could try out as well. But Jupyter, again, in a notebook, a lot of people like to develop code in Jupyter notebooks, but I don't really think of it as an IDE the same way that some of these other things are, and I find it more useful for sort of documenting things and working through scenarios rather than sort of developing code that I'm trying to get working. I just want to pivot for a moment to outside of the notebook to a terminal, because as I said, we can we can, oh, and in order to do that, right, I need to pause my session here. Somehow my terminal seemed to have gotten lost, but we've got it here. So what I have here is I'm sitting in a terminal, and I put some code, basically the core piece of code of not the object-oriented version, but sort of just the function-based version of the cipher that I wrote. And so there's no markdown in here. There's no notebook. It's just pure Python source code that defines the encoder and the decoder and the transformation function. And then after those definitions, then it runs a few of these things. It encodes it and decodes it. But for example, now I can, if I want to run this program, I can just say Python cipher.py, and it then runs through it executes all these things, and then it prints out. What I told it to do was print out 3 messages in these 3 print statements here, and so it prints those 3 things out. And again, this is a very short program, but if I were, running some scientific computation that maybe takes a few days to run, I would just sort of run this. I'd put it in background. Maybe if I'm on a system that's got like a batch queuing system, I would submit this as a batch job, and it might open files and write new data, data to other files. Somebody has, David Lewis noted that Google Colab is also great, no installation, in the Google Suite and free. Right, so this Jupyter notebook that I'm running right now, I'm running on my local laptop, which fortunately didn't burn down during the potential fire. But Google Colab is a cloud resource that Google supports that allows you to run Jupyter notebooks on their resources. It's in the Google Suite and it's free, so it's true. With Google, you can access data in your Google Drive very, very easily as part of that. It's free as long as you don't need to do something too long running and onerous. So if you start running very long jobs in Google Colab, it'll start asking you if you're still there, and if you're, the resource is not intended for long running programs, but it certainly is. And I think Christopher Cameron in the upcoming talk on Jupyter Lab will probably mention that, even though he may be using a different system for that. So I ran this Python program, and it ran to completion, and then it returned control to the terminal. But for example, one thing I could also do is that I could start up IPython, which is this interactive session, and I can use this magic function run to run the code, and then it runs it and it prints the same messages. But now it's left me within the interpreter still. I'm still within the same interpreter. In fact, everything that got defined in that program is accessible here, and I can see what's been defined and information about those things with this who's magic function. So I see all of these things that I defined in that function. I have the encoded and decoded messages. I have the dictionaries that implement the encoding and decoding. It doesn't print out the whole dictionary. It just tells me there are 52 elements in it. I have all the letters. I have the string module that I imported. That is a module. That is another type of object in Python, but it's just there, and I can access out data within that module. And then this transform message function that I wrote is also there, and it's a function is an object like anything else. It can be passed around. It can be manipulated like anything else. And so this is very useful in that you're doing things in IPython, or you can do the same kind of thing in a Jupyter notebook. I can run this thing, but then I could, since I have all these things defined, I could, for example, transform some other message. I could transfer hello world according to this encoder, and I would get back some other encrypted thing. So all of these different environments, the core Python interpreter, the IPython console, the Jupyter notebook, they all work together, but they sort of serve different use cases, and it's up to you to sort of figure out. And often, for example, if you're working within an IDE, it'll be something like the IPython there'll be a console window as part of the IDE that's running IPython that lets you sort of interactively work with your code and your data. So I'm going to stop there, and I'm going to go back to the talk, and we pivoted to the terminal. And now, just in the last little bit, I want to talk a bit more about Python as a software ecosystem. I've been focusing on the language, which provides a substrate for us to use all these different programming constructs to define functions and classes and different types of control flows. And I can also use that same language for importing and using functions that are defined in external packages. And there are many thousands of external packages that people have developed to support all sorts of different tasks. So we can talk about it as a single ecosystem, or we can think of it as really multiple ecosystems that are used for different tasks. And so, for example, a lot of operating systems have found Python to be very useful as an environment for scripting various kind of sysadmin tasks. And there's an OS module as part of the standard library that lets a Python program interact with the operating system and the file system and do various things. There's a rich set of tools for web programming and website development that a lot of people have developed and used. So a lot of websites running are in fact running Python under the covers because they support a lot of different useful operations. There are a set of packages that allow you to build, say, graphical user interfaces if you don't want to necessarily be having people have to work through a command line interface. If they want sort of a more graphical user interface, there are packages that support that. And then there's a very rich environment for scientific computing, for data science and machine learning. And then that's really sort of my focus. And again, I'll be giving a talk in early November talking about this Python ecosystem for scientific computing and sort of what some of the core components of that are in more detail. It's worth noting that as I said at the beginning, that Python is an interpreted language, so it's inherently slower than perhaps equivalent compiled code. But in fact, a lot of these external packages are in fact written in other languages. They're written in compiled languages such as C or C++ or Fortran, and they're callable from within Python by what's known as extension modules. So by using a compiled library underneath that's fast and sort of accessing it in an appropriate way, I can have all of this kind of the nice high-level expressivity of the Python language. But then when I make calls down into these libraries, these numerical libraries, they operate much more quickly over big data sets for better performance. And I'll talk more about that in the upcoming talk. And yes, and David has mentioned both NumPy and Pandas as being two examples, two very widely used external packages that are really sort of at the core of this environment for this ecosystem for scientific computing and data science. And so this is just sort of a graphic kind of showing, right? So I'm giving this talk on November 1st, Scientific Computing with Python. We're sort of building up from the core Python language and this, I haven't mentioned it here, but this application programming interface that lets Python talk to C and other compiled languages. We can sort of build up things like NumPy and SciPy and Pandas. So there's a rich developed set of tools for doing scientific computing and data analysis, for doing big data visualization. These things talk to each other and work and are well integrated with each other. There's a number of tools that have been developed in Python to support machine learning. A lot of the kind of the deep learning libraries that are sort of at the core of a lot of what we're hearing about, with AI these days is using things like either TensorFlow or PyTorch, which are Python APIs over compiled code that is very performant for large machine learning models. And so I'll be talking more about some of the tools in this system, in that upcoming lecture. I did want to say a little bit about installing Python associated packages because it's something that it's sort of it's kind of a nuts and bolts detail that comes up in a lot of contexts. So I mean, you need to have, if you want to run, say, on your local machine or run on some remote machine that you have access to, Python needs to be installed, and whatever packages you want to use need to be installed. Your machine might already have a version of Python installed, but it might be one of these things that's part of the operating system. It might be, say, in /bin or user bin if you're on a Linux system, and it's probably being used for system administration and sort of routine tasks on that machine. So it's best not to mess with that one. don't start trying to update it or add other packages, or you don't want to mess with your operating system. So it's best to sort of install a different version of Python that you can sort of play with without necessarily messing that up. It's possible that there would be a version of Python installed that's been installed by sysadmins, a separate version that's not part of the OS, in some centralized location for multiple users. But it might not have every package you need. And part of what I'll describe here is how we can install additional packages. Fortunately, multiple installations of Python can coexist on a single machine, and any given installation sort of internally knows where to look for packages. So for example, in any Python interpreter, if you import the sys module from the Python standard library and then print sys.path, you can see all the directories, all the folders that Python is going to look through when you try to import something. And so that's often a very useful way to figure out, okay, where does this version of Python that I'm working with, where does it expect to find things, and why isn't it finding something I'm trying to import? There are lots of kind of if you install just sort of a bare bones Python installation, you'll get the Python interpreter and you'll get the Python standard library, but you don't get much else. And part of the power of the whole ecosystem is that you have access to all these other packages. So there are different kind of bundled Python distributions that sometimes get described as batteries included, from a number of different organizations that install lots of additional third-party packages. And the Anaconda Python distribution is probably the most popular of those. But by default, it installs a large number of packages. And this might not be really what you want. So as I say here, one big Python installation might be convenient, but then it can also start to suffer from incompatibilities among packages. It might be that there's different version requirements depending on different things you need to be able to do. And for sysadmins who are trying to support multiple users, that can be difficult to maintain. And so what's available instead, and which I myself use in my own work and recommend, is it's generally better to create smaller kind of focused environments for different problems and use cases. And these are essentially kind of walled off installations that have just the set of packages that you need for any given task. And so, for example, on my system, I've got maybe 40 different environments that I use for different kinds of projects that I work on, or for testing different things. And again, those are all walled off from each other. They don't trip up on each other when I try updating some package or what have you. So for any Python installation, there's a module within the standard library called venv, that allows you to create a new virtual environment, one of these walled off installations. And then you can use what's known as pip, which is a package manager that you can use to install packages into that environment. Alternatively, there are Conda-based installations, which use a package manager called Conda. And this comes if you were to install this big Anaconda Python distribution, you'd get Conda, but you can also install what's known as mini Conda, which is basically just the package manager itself and a few other tools. And I'm going to show you sort of what that looks like in terms of using it. So again, Conda is a package. So by default, I've got Python, but I don't have NumPy, I don't have Pandas, I don't have Jupyter, I don't have Matplotlib, I don't have all the things I might want. And so Conda is a package manager that can install Python packages, and also perhaps compile things in other languages that you might also need. And mini Conda is kind of a minimal setup that just installs Conda and some of these supporting tools. And then, as I say, it's up to you to build whatever environments you need to suit your needs. You can install packages from different channels, and you can specify different version numbers and requirements. And there's various ways you can create these things. So, for example, if I wanted to create some new environment, say that just has some of the core elements of this scientific computing ecosystem, I could create a new environment named PySciCore, in which I want to install Python and NumPy and SciPy and Pandas and Jupyter and Matplotlib. And in fact, this Jupyter notebook that I'm running is running in an environment that I created with that command there. And then once I create it, and all these packages get installed, I can activate it. Alternatively, I could create the thing first and then install packages afterwards. Maybe I need to install in this other environment, I need to grab stuff from a different channel, such as the Conda Forge channel instead of the default Anaconda channel. But I can do that, and then there's a number of commands using the conda command on the command line that I can use in order to say list all my different environments, or list all the packages that are currently installed in an environment. Or one of the nice things about these is you just sort of mess up, and it's very easy to just remove an environment, just trash it and start over again if you mess up somehow. So I could remove an environment, or I could update things. I have here this is something I downloaded from the conda.io website a while back. It's a cheat sheet, and so this kind of thing is very useful if you're saying, oh, how do I clone an environment so that I can then make some, not ruin it, but make some modifications to it. And so there's a conda create clone command. There's a can create environments from YAML files that basically tell you about all the different packages. So I certainly, if you're on a conda-based system, I'd encourage you to try creating environments that sort of support whatever it is that you need to accomplish. You might be on a different system where there's a Python installation, and then but not necessarily conda, but then you can create sort of equivalent kinds of virtual environments using this venv module. And this looks kind of similar. I can create a new environment called PySci-Core. This is using Python, so this sort of bootstraps off an existing Python installation. I can then activate that environment. I can install packages. I might want to upgrade this pip package just because sometimes that gets out of date. And then I can go in and I can install the packages that I want. And again, in both of these cases, I have a thing that just has the packages that I've asked for along with whatever their dependencies are. And then I can, if I decide I want to do something different, I can create a new environment and activate that. And again, I'm doing this on a regular basis in my own work. I'm sort of jumping between different environments that I activate for different purposes. So I hope I've given you some sense, and I appreciate all of those who stayed past 10 o'clock with our fire alarm. Giving you some sense about how Python, is both an expressive programming language that lets you craft whatever custom analysis you need. I guess I didn't make the point, but I want to make the point that, and I'm contrasting this as opposed to saying working in some environment where you have sort of a predefined set of things that some other developer has decided you can do, right? There's a set of functions you can maybe click from a menu or work in a GUI, but by having a full expressive programming language like Python at your hands, you can really create, you're not beholden to whatever anybody else thinks is the right kind of analysis to do. You can write that yourself, but at the same time you have this really elaborate and well-developed set of interoperating packages and libraries that allow you to process data, to engage in various kinds of scientific computing for whatever it is that you need to do. In terms of resources, there's a lot of useful documentation and tutorials on the python.org website. I mentioned if you're interested in learning more about Conda, you could go to the conda.io website. Within the Center for Advanced Computing, CAC, we have a large set of topics as part of what we call the Cornell Virtual Workshop about lots of, this is sort of online training materials for you to work through on your own, covering a number of different topics in scientific and numerical computing. And I've listed just a few here that are kind of relevant to Python, which you could go to the main CVW site, look through the roadmaps, and that would be another place to learn about how some of these Python tools play out in detail.